The Jacobian matrix is a fundamental tool in multivariable calculus that represents how a vector-valued function changes. For a function mapping from n dimensions to m dimensions, we write it as a vector of component functions. The Jacobian is an m by n matrix of all first-order partial derivatives, where each row represents one output function. To calculate the Jacobian, identify variables and functions, compute partial derivatives, then arrange them in matrix form. Let's find the Jacobian of this two-dimensional function with components f1 equals x squared plus y squared and f2 equals 2xy. For f1, the partial derivative with respect to x is 2x and with respect to y is 2y. For f2, we get 2y and 2x respectively. Arranging these partial derivatives in matrix form gives us the Jacobian, a 2 by 2 matrix with 2x and 2y in the first row, 2y and 2x in the second. For our second problem, we have a function mapping from 3 dimensions to 2 dimensions, so our Jacobian will be 2 by 3. For u equals x squared y plus z, the partial derivatives give us 2xy, x squared, and 1, forming our first row. For v equals xyz, the partial derivatives give us yz, xz, and xy, forming our second row. The complete Jacobian is this 2 by 3 matrix with our calculated partial derivatives arranged by row. Geometrically, the Jacobian describes how a function transforms space, showing how regions are stretched or compressed. The Jacobian has many applications including coordinate transformations, optimization, neural networks, robotics, and physics. Remember, each element is a partial derivative of one output with respect to one input.